Greetings and welcome. We are still dealing with the nature of data, the different forms of data that are supposed to be analyzed, processed through the data science cycle or pipeline, a life cycle or pipeline that we have emphasized in the past. Remember the type of data you have been collecting throughout your 2 decades of life, assuming you are 20 years old, are various forms. You have had taste, you have had a skin touch, you had excuse me, you had the voice coming to your ears, you had images and video and clips coming to your eyes. All of those are processed in a very complex unit of your body called brain, and depends on how they have been translated and transformed. You would understand a very specific image as your the face of your mother or your father or someone that you know, a car maybe, or a pet that you love. Okay, so that was a natural data that we have had in the past 2 decades. Now we are talking about technical data in a sense that they are coming at you in a different form, such as numbers, such as images. We want to understand the data. So briefly, we are going to discuss the nature of the data. So let me share my screen. As I'm going to share my screen, we are going to go through the part 2 of session 3, where we are discussing about numbers, vector of numbers, and representation of data. If you take a look at this slide, we have a vector at the left-hand side. This is kind of vertical vector, I would say. As you have watched in the remedial clip supplied earlier in the sessions, you're going to have one column and 3 rows. That's a vertical vector. You could potentially have a horizontal vector where you have 1 row and 3 columns and 3 numbers separated by a comma. Vectors are typically known to be 1 column and multiple rows, or 1 row and multiple columns. Now, if we put together different vectors of the same size together, then we are going to create what we call a matrix. A matrix is a collection of vectors. You have 10 rows, and you have 10 rows, and you have 15 columns, for example. And this is especially quite visible when we go into representing an image in the form of a matrix in the follow-up session. So that's a bunch of numbers. X1, in this case, we mean 5.2, X2 is 9.8, X3 is 2.5, something like that. It's a collection of numbers represented in the form of a vector. Now, most of the time, we are quite comfortable visually to see things. Our brain can actually effectively process, think more creatively, if the data is presented to us in the form of a 3D space. 4D is not easy for us to imagine. We are going to get to the 2D in a moment, but 3D is really nice to imagine. We are going to see where everything is going to land visually on a place, on a space. Now, this is also called a vector. This is a vector in a sense that it has a length and it has angles to horizontal plane. X1, X2 is considered a horizontal plane, and X3 is going to be a vertical axis. So it is going to have an angle to the horizontal plane, and it's going to have an angle to the vertical axis. So if I wanted to see my place in that 3D space, I'm going to imagine that I have a vector, and the vector is originated from the 0, 0, 0, the origin of the axis, and then it's going to have a direction, it's going to have a value, and it's going to have angles. That would be a bit too much of information sometimes. So what I would do instead, I'm going to say that these numbers we just spoke of, 9, 5, 3, whatever you have in mind, is actually the end point of the vector. I'm assuming it is originating from 0, 0, 0, and if I have the end point, then I'm going to easily visualize that in a 3D space. And even if it is anywhere in the space, you could potentially shift them and bring them and rest them at the origin of the axis. So in order for me to represent this vector in 3D space, I'm going to say that, tell me about the shadow of the X on the X1, the shadow of the X, bold X, on the X2, the shadow of the X on X3, 9, 5, 3. Remember those numbers? So that's going to allow me to actually represent this vector in a 3D domain. So that's a 3D space, okay? Excuse me. The next one is going to be a scatter plot. It's a 2D plot. Now, as you can see, I put together black, basically signs together. I have kind of a orange, yellowish objects together in class 3, and I have kind of a gray, green in class 2. I'm going to spread them. So if I wanted to show you a simple example of what this scatter plot looks like, it actually looks like your kid's room when you were a child and you were playing with so many tools and toys and everything is spread across. This is not properly placed. Obviously, this is not going to be really as much helpful. But remember, if you happen to have a kind of a scatter plot where everything is in their rightful place, for example, you have everything in this shelf, everything in here, and everything is here, is exactly like what we are trying to do. We are going to actually put together objects, but you need to be very careful in terms of selecting the features. Now, it might be funny to state that at this stage, that if you go to a messy room, you could potentially go into a different angle and you could potentially see everything in the right place, maybe. I'm just making an example so that it actually clicks in your mind. So it really is important for us to know what the feature is going to be. And if you are not selecting the feature correctly, then this is going to really look like a messy scatter plot. And you have seen that in the lab in the past, okay? Let's take a look at the feature vector, feature space, and feature set one more time. Feature is a list of numbers, for example, age, name, and height, and so on. So this, as you can see, I have to be very careful in selecting my features. I'm going to have petal width and petal length. This is about iris flower. Let me tell you what iris flower is, just in case that we may not know this in our own languages that we are so familiar with. This is iris flower. I don't know what it is pronounced in your different languages you are accustomed to. So this is iris flower. And if you take a look at iris flower, they actually have features. For example, there is going to be petal and there's going to be sepal. And the separation of petal and sepal is that those who are very fresh, like very close to the internal body of the flower, is called petal. Those that are looking like a leaf, actually extending outside, they are called sepal, right? So let's take a look at this one more time. I think I have. So take a look at the petal. The petal has, you see, these are very fresh. They are not aged yet. They are not mature yet. Very nicely connected to the root of the flower. And these are actually leaves. And these are different. We call them sepal. So petal, you have a length and you have a width. And you want to classify iris flower. A very simple lab if you wanted to do it. Now, again, there are many terminologies. We don't want you to go deeply involved, be involved in the biology of a flower, but there are some different terminologies such as veins. They really look like human veins. and you have the falls, which are actually coming to the end. This potentially where the water is, the water could potentially come all the way and fall off the leaves side. So I just wanted to give you this feeling what the iris flower is and what the petal width and petal length is. I have come across as an expert person, for example, I'm not an expert, I'm just pretending to be one, that the petal width and petal length are really nice feature to classify iris flower. So I'm going to say that these are my features: petal length and petal width, okay? Feature vector are actually every row of the table. So 5.1, 3.5 is a feature vector. 6.3, 2.5 is a feature vector. Feature space, I just need to understand how I'm going to be representing it. Petal length is on the horizontal axis, petal width is going to be on my vertical axis, and I'm going to actually put my dots, meaning perhaps different types of iris. Again, I'm not an expert. So 2 of them are going to be here, 1 of them is going to be here, and 3 of them are going to be collected together on one side of the feature space, okay? And a feature set is actually the help to predict the output variable. So basically, I'm going to actually use the feature, and the feature set is going to be basically when I pair the features. So here I have petal width and petal length as 2 separate features. When I pair them, that becomes feature set. So I could pair 5 features, and that becomes my feature set. So you need to keep that in mind. Feature is a single attribute. So that's a single attribute: petal width, petal length. And feature set is the paired feature together. The feature set could potentially be just 1 column. It doesn't have to be 1 attribute. It doesn't have to be necessarily 2 or 3 combined and paired together. For example, I want to predict the age of particular person. We need to know the year of birth for. So obviously the feature set is just the year of birth. So this is my feature set, this one, because I'm going to actually extract that using so many other information available, perhaps provided by the user or the entry of the system. Let's take a look at feature space. Consider one of example: thickness of the car tires after some testing period. So you have tested, you have put the car onto the tarmac, and you started basically testing the tire, or just the tire potentially. It doesn't have to be the car. You basically rotate the tire on the ring, and you want to see how much thickness is left. Distance traveled in the test, of course, it is rotating on its own axis. It's in the test lab, in the lab room, but you can still calculate the distance that the tire has traveled. Time duration of the test, you know how many times it has been running and how many times it has been stationary and basically stopped rotating. Amount of chemical C in tires. We are not talking about the type of chemical, but it could be anything that. So the feature space is the positive quadrant in R3, X1, X2, and X3. And the expert knowledge is going to tell us whether the speed of the vehicle that has been moving, is it going to be important or not. So we need an expert knowledge. This is where data scientist is supposed to be separated from a simple programmer. Who basically takes an algorithm that might have been well defined through a flow chart, and then he or she is going to perform the data. Data scientist is supposed to be a scientist, meaning, okay, what am I looking at? What is it that I'm trying to do, okay? Now this becomes extremely important because what kind of feature do you want to consider? I mean, for example, if you take a look at the iris flower, are you going to talk about the color? Are you going to talk about the height? Which one is really important in the classification of the iris flower. Let's go back to the iris flower that we had. So this is iris flower. So how do you want to classify? And as an expert, again, I'm not an expert in this domain. As an expert, you need to go back and say, okay, this is what I need. This is the type of information, the type of the pieces of data that I need. Let's take a look at me. I have a fever. Do you want to look into my skin color when I have a fever? Or do you want to take a look at the redness of my eyes? Do you want to take a look at my hearing? Could be, but not necessarily immediately. Or my smell, maybe, as it is true in COVID-19. Or you would like to take a look at my heartbeats. This is the moment that you could potentially go wrong. This is the place that you need to pick up the right feature to assist you with the follow-up processing and eventually successful classification at the end of the process. So you may potentially be the one who is going to combine in some of the features, pairing some of the features, and eventually getting to the right place to move on. I'm going to stop here, and then I'm going to have my second recording on the next stage.